Good afternoon, everyone. My name is Jorge Lopez, and on behalf of my teammates, Laurent, Nicanor, and Alain, we want to thank you for attending to this presentation of the work entitled Towards Agent-Based Modeling of Crop Irrigation. This is a work developed under the joint agreement between University of Mons and Universidad de los Andes. In the context of a global need to increase food production and the general concern to make it in a sustainable way, basically related to the reduce of freshwater consumption for irrigation, we developed this work. The main motivation of this work is then to develop a mathematical and practical tool to help to increase the productivity of crops by using a relatively new approach and taking advantage of the new data sources. This tool must be suited to work in a closed-loop control system. However, the challenge is to deal with land heterogeneity and environmental variations, namely climate change. The proposed outline is as follows. We already begin with the motivation. Then I'm going to introduce the ABM framework, providing a justification and a description of agents. Then we set a case study to test the model and to present some features. Afterwards, I'm going to show you some results under different scenarios. And finally, I will give you the most important conclusions. An agent-based model is a model composed by individuals. Those individuals, we will call them agents. An agent is an entity with properties and characteristics that allow it to interact in an environment with other agents. The main characteristics of agents are that they are identifiable, so they are part of a discrete set. They can act asynchronously, so they can make actions that are not related to the time of the other agents. They can be different, so they are heterogeneous by definition. They are space aware in their environment. They are able to make autonomous decisions and independent decisions. And finally, they can interact with the environment. The general structure of an agent is composed by two levels, an upper level or a macro level and the lower level or micro level. The upper layer is where the decisions, the management requirements, and the agent-to-agent interactions are. And the lower level is where the physics, all of the dynamics, internal processes, and environmental interactions are. In these applications, we define two kinds of agents. A crop soil agent, which is composed by a patch of soil and the crop on the top of them, and an irrigation agent, which is interacting with all of the crop soil agents. And there are environmental variations that are interacting with all of the agents. But why we choose agent-based modeling to face land heterogeneity? Okay, there are a couple of reasons for that. But first, we need to define what is land heterogeneity. Land heterogeneity could be related to the soil, and the properties are changing, of course, with depth and also across the surface. But also, the land heterogeneity is related to the topographic situations of the crops. If you look at the pictures, there are three possible situations. Most of the cropping lands in Belgium are flat, but in the other parts of the world, the agriculture is driving in a different topographic scenarios, as in the side of the mountain or also in a bumpy lands. Then this heterogeneity could be related to the main soil properties. For this application, we are just considering the flatland scenario. And the main property which is changing is the root zone depth, theta 5. Then all of the agents have the same properties, the same lumped parameters, but the root zone depth is changing. It defines the capacity of holding water for every agent. If we consider the other topographic scenarios, there are also another interactions between agents. As if we can see it here, the red arrow is indicating that there is water going out of the highest part of the terrain to the lowest part. And this is the same situation in the bumpy land. So the lower level of our crop soil agent is defined by this dynamic equation. The evolution of the system is related to the state variables, the environmental inputs, which are the reference evapotranspiration, the precipitations, the air temperature, the solar radiation, the minimum and maximum temperature, and the atmospheric CO2 concentration. There are an independent input, which is the management input named irrigation, and there is a set of parameters, which is theta, and the model is supposed to advance daily. The set of state space equations are based on the model proposed by Wally and others in 2012 and the model proposed by Xiao and others in 2018. The first state space equation, which is related to the water content available in every patch, it's a mass balance equation. The fluxes going out of the patch of soil are the crop transpiration, the surface runoff, the deep drainage, and the fluxes going in are the rainfall and the irrigation. Second state space equation is related to the cumulative temperature, and the third state space equation is related to the cumulative temperature until maturity, and there are two functions there, H2 and H3, that are functions related to the negative effect of having a lot of temperature and the negative effect of the lack of water. And the last state space equation is related to the biomass, and is where the function g is taken into account, and this is a nonlinear function of the growing. This g function is composed by two logistic functions, which are related to the temperature needed for the full development of the crop, which is the theta 18 parameter. And this function, there are the other two state variables included, x2 and x3. This is the main function that relates the full growing of the crop, and is where the nonlinearity has the most important impact. Now, once we conclude the definition of our crop soil agent, we need to set it in the context of a control system and define the irrigation agent, which is linked to the crop soil agent by the signal U. The irrigation agent is intended to implement optical irrigation strategies. These strategies will balance the water consumption and the biomass profitability. For this work, our irrigation agent will implement two irrigation policies. The first one is based in the maximization of the biomass produced by the crop. And the second one is the maximization of the production, the maximization of the biomass, and the minimization of the water consumption. The first irrigation policy also takes into account that there is a limit in the maximum water that could be used for irrigation daily. And the second one also will consider the maximum available water every day. Well, to test our model, we defined a case study. We selected a field located in the province of Brabant Wallon in Belgium, and there is no meteorological station there, so we collect the data from the meteorological inputs from the station located 11 kilometers north of the field. You are watching the environmental inputs, which are the temperature, maximum and minimum, and average, the solar radiation, and the daily rainfall. And the reference evapotranspiration is computed by using the FAO CropWatt software. After the selection of our field location, we continue with an image processing to define agents. We start with an aerial capture of the field. After that, we apply some color to gray conversion, then edge detection in order to limit the area of interest. After that, we apply binarization. Then we plot a grid over the binarized image. After that, we assign the agent based on the amount of area that it is inside of the grid related to the area in the binarized image. And after that, we build a directed graph, which is very important when we are trying to relate one agent with these neighbors in the program. One of the main advantages of this framework is that we can change the size of agents in order to have a better interpretation of the field behavior. To doing that, we can select a different grid and then a different agent assignment. And you can see in this example, we have 66 agents instead of 16 agents. And at the right side, you are watching the undirected graph of this assignment. This is one of the main advantages of this framework. However, for this particular case study, we selected the first assignation of agents, which is based on the 16 grid assignment. And you are watching the roots on depth of the 16 agents, which is the only parameter that it is changing, and that is the characteristic that make them different. Now, to implement our ABM, we made some assumptions. The first one is that the sowing day is the same for all agents. The next one is that the size of the patches is based on previous information. The third one is that the crop on all patches is width of the same cultivar. And the last one is that the harvest day is the same for all patches. Now, in the flatland topography scenario, we define 5 cases. The first one is no irrigation. The second one is with a fixed scheme of irrigation, which is a common practice in agriculture. The third one is applying our first irrigation policy. The fourth one is when we apply the second irrigation policy. And the fifth one is applying our second irrigation policy with some uncertainty in depth and precipitations. On the right side, you are watching the performance for the first state space variable for the fixed scheme of irrigation in green line. And also you are watching the pattern of rainfall in red. And in the bottom graph, you are watching the first irrigation policy, which is basically applying a lot of water just 2 days. Here we have the performance of the 4 state space variables for a particular agent, which is the agent number 4 in our grid assignment. The first graph, which is the water content in soil, is showing us that the case where there is no irrigation is the bottom line, and when we are applying our first irrigation policy is the top line, the green line. And with the fixed irrigation scheme is the CM line, and in the stripe of the middle are the cases when we are penalizing softly the water consumption or strongly the water consumption. The second state space variable is not changing because the temperature is the same for all agents. The third state space variable is showing us that when we do have a lack of water, the state space variable will increase. When we have enough water, the state space variable will not change. And in the last graph, we are watching the biomass production, which is clear that when we don't have enough water, the production will be low, and when we have a lot of water, production will increase. And if you take a close look, you can see that the yellow line, which is indicating the case where lambda is equal to 0.1, is close to the green line, which is the production of biomass when we are applying our first irrigation policy. Now we can set a comparison at the end of the cropping season by setting our no irrigation case as our base of comparison. Then we have when we applied our first irrigation scheme, which is the fixed one, we have an increase of 70% of the production. And when we apply our fixed irrigation policy, we increase our production in 95%. And then when we apply our second irrigation policy, but with soft penalization, which is lambda equal to 0.1, we increase our production in 93%. But when we apply a strong penalization, which is lambda equal to 100,000, our production increases just 15%. But what is interesting here is when we apply a fixed scheme of irrigation, we are using 340 millimeters of water per patch. When we apply our first irrigation policy, which is not taking into account the water consumption, we use 70% more water. But when we apply the second irrigation policy, we are just using 14% more water than in the fixed irrigation scheme when we apply a soft penalization on water consumption. But when we penalize a lot the water consumption, we can reduce the water use and having 15% more production of biomass than in the no irrigation case. Afterwards, we apply our second irrigation policy, but including some uncertainties, mainly related to the root zone dip, which is selected from an uniform distribution, the adding of some noise in the meteorological inputs, and the selection of different sowing day in a window of 8 days. And we are watching that the performance applying this irrigation policy, but with the noise and the uncertainties, uses less water than the first irrigation policy, but also the performances indicates that the production of biomass is less than the production with a lot of water. But here we have the cumulative irrigation, and it indicates that the water used for irrigation is lower than the water when we don't have any penalization for water consumption. And then we made an improvement in the second irrigation policy with the inclusion of a sliding window of a prediction horizon to include a forecast capability in the optimization cost function. And we are watching the total irrigation for different lambdas and for different prediction horizons, and the maximum biomass for different lambdas and for different prediction horizons. And the best combination occurs when in the total irrigation column we are close to the bottom line, the bottom black dashed line, which indicates the lowest irrigation possible, and in the maximum biomass production when we are closer to the black dashed line, which indicates the maximum possible production. And that's the case when lambda is equal to 0.01 and HP is equal to 8 days. And with this combination of values, we apply the second irrigation policy, and we do have this forecast of irrigation. And as you can see, the red dashed line indicates the final irrigation, and the full colors indicates the forecast of irrigation. And in comparison with the scenario number 3, which is when we apply the first irrigation policy, which is just considering the maximization of the production, but not taking into account the water consumption, this improvement of the forecast window is saving around 10% of water, and the reduction of production is just 1%. So it's a good trade-off. Finally, the main conclusions of this work is that agent-based model proved to be a flexible modeling framework to face heterogeneity in agriculture. As this model was coded in MATLAB, we face a lot of issues with the asynchronous event, and we are working now in the implementation of this model using Repast, which is based on Java, and Mesa, which is based on Python. The irrigation agent requires the knowledge of state variables that are not measurable directly, which is the case of the X3 state variable that indicates that we need to implement an observer in the loop. And the last one is that this model doesn't consider the negative effect of the excess of water. And we included this negative effect in the current version of the program. Thanks for attend and watch this presentation. And if you have any comment or question, you can write me an email to the addresses on the screen.